Joking about how bad a car is aerodynamically by calling it a brick is common. Rarely do we get the privilege of actually witnessing what it looks like in its most literal form. The 1965 Meyers Manx Buggy shaped popular culture as much as the VW Beetle, which the drivetrain was taken. This low-powered vehicle exhibits surprising performance due to it weighing relatively very little. As a dune buggy, it would rarely reach speeds that would present a higher aerodynamic drag force than the mechanical forces from the sand. So this simulation of it travelling at a highway cruising speed of 30 meters per second is outside of its intended purpose. Anyway, here we are measuring a drag coefficient of 0.88. And if you think that is bad, the lift coefficient is positive 0.75. Now, coefficients aren't very relatable, so in kilograms, that's about 50. Just to make this sound even worse, 40 of those are lifting the front axle. The weight of this vehicle is considered light, with safety features including it's okay if you fall out, you're landing on sand. The weight is around 5 to 600 kilos. I don't know the weight distribution, but going by the engine being behind the rear axle, there is a minimal amount of weight on the front. I'm going to say between 30 and 40%. That is between 150 and 240 kilograms. That's a bit of a range, but removing 40 kilograms from that range means steering at highway speeds is more of a vague suggestion. This is for a number of reasons, including larger tyres at the rear giving more grip, and with the car needing 17 kilowatts of power to push through the air, the front wheels would need to overcome those forces. Now, using 17 kilowatts of power doesn't sound like a huge amount these days, even though you'll be seeing that in fuel consumption, travelling at 30 meters per second. These cars only had around 40 horsepower, which is 30 kilowatts. That's taking the popular view of the available power. It is more likely they had about 25 kilowatts. So that means there's only 8 kilowatts of available power to go up a slight incline, a 2.89% gradient. Now, I'm not happy if I haven't made something aerodynamically better. I'm going to proceed to make myself happier. Normally, aerodynamic issues are located at the rear. This has the problem just here. To start, I'll note the air inside the cabin, put most appropriately, is violently assaulting its occupants. The flat windscreen is providing a degree of protection from the air trying to remove their faces. I'll make changes in this area later. For the moment, the front is the biggest problem. The front has a large high-pressure field that has air accelerating over the top of the bodywork, creating the lift. Therefore, the first improvement was to continue the bodywork under the front and floor, and then to the sides. This just made use of the high-pressure field that was already present and accelerated it under the front as well as over it. Drag was reduced by a few percent, but the lift was more than halved, distributed evenly front and rear. Next, a radiator inlet was added, positioned in the center of the high-pressure field and dumped out the top in front of the windscreen. Removing the lights is a bit of a cheat, but for following body modifications, it makes more sense. The hope for the inlet was to create an air curtain of sorts for the windscreen. It seems to have worked to some degree. A further 10% drag reduction is unlikely to have come from the lights alone. A 20% reduction of lift to a now more sensible 150 newtons of lift at the front is caused by the high pressure on the front. The high pressure mapped on the front surrounding the outlet wasn't expected, but most of this car is aerodynamically unexpected. Adding bodywork to the wheel arches and a curved windscreen was intended to reduce the drag further, but it didn't change anything. Comparing the bottom pressure map, the front has now significantly more low static pressure, a difference of lift of more than 200 newtons. Now there is 60 newtons of downforce, and overall the car has no lift. This large reduction of lift is likely the reason for the absence of drag reduction that the curved windscreen should have given. I mean, the windscreen is now creating thrust. Winglets were added to deflect the air around the wheels, but didn't. They just increased drag. That addition, along with the diffuser, contributed to more downforce. Here, the side windows is the single most effective addition for reduction of drag, removing 12% from the previous model and achieving the lowest drag number. From the initial model, the drag is reduced by 24% to 463 newtons at 30 meters per second. Now this requires 14 of the 25 kilowatts, giving the car the ability to drive up a 4% climb at that speed. Lastly, assuming the winglets counted for all the drag of the 30 newton increase seen between the 4th and 5th simulation, removing that gives the potential of a coefficient of drag of 0.67, which is just really bad instead of horrific.